So we have 5 technical talks. And so this morning, the session is about advance in binary program analysis. It will arrive.
Okay, I can stand now. Okay, cool.
So first talk is about lifting NVIDIA GPU assembly to LLVM IR for downstream security application. Please.
Good morning, everyone. My name is Junpeng, and I'm a PhD student at Purdue University. Currently, I'm in my 3rd year. And today, I will present our work, NVLift, lifting NVIDIA GPU assembly to LLVM IR for security analysis. So let me introduce a bit about the background. So as we can see, here is the CUDA source code. It contains the CPU code and the GPU CUDA kernel. And then we can use NVCC to compile it to binary. It also contains the CPU binary that will be executed by CPU, and also BPA-X is a higher level of assembly code. Then it can be further compiled into SAS, which is the lowest level assembly code that will be executed by GPU. And so we found that SAS is undocumented, and it's kind of mysterious for researchers to do the binary analysis. So that's why we propose our work, NVLift. We try to bridge this gap a little bit. And so here's the overview. But firstly, we need to understand SAS instructions. Then we can do some analysis. So in the second step, we build a lifter. We try to translate from SAS to LLVM IR, and then we can do some security analysis. And so the reason we target LLVM IR is that there are a lot of tools based on LLVM IR, and like the Karel for symbolic execution and RegDAC for decompilation, stuff like that. Then for security analysis, we use decompilation as a case study. So to implement such a work, there are a lot of challenges. The first is that we don't have enough official documents from NVIDIA. There is only a very sketchy SAS documentation. It introduces the function of each opcode and the types of operands like that. So it's not enough. The second problem is that, as we can see for SAS instructions, there is no type information. But if you want to translate it to LLVM IR, we need the types. So we need to figure a way to figure out that. Then also after the lifting, we need to check the correctness. We don't know if it's wrong or correct. So I will solve these challenges during the discussion of our work. So for the first step, how to understand the SAS instructions. So for the firstly, we will try to compare the opcode from BPA-X instructions, because even there is no documentation for SAS, there's a lot of documentation very detailed for BPA-X. So they are not one-to-one mapping, but by checking the opcode for BPA-X, we can still get a sense of the functionality, the usage, and it's not enough. But the good thing is that there are a lot of reverse engineering work, like papers and blogs. So they are not exactly what we want, but we can have better understanding of the format, usage, function, and then we can have assumption for each instruction. Then after that, we can just verify the instructions by CUDA-GDB. Here's an example for SAS assembly. RMAD is for multiply and add. It will multiply R2, R3 plus R4, and then write it back to R2. Okay, so this is the design of NVLift, and I will break it down step by step. So first step is to extract SAS from CUDA assembly, CUDA binary. And NVIDIA already provides some tools like CU OptiJump and NVIDIA this ASM. So after extraction, it will be like this. So it's a demo for ReLU operator. And second step, we just press the SAS extracted. Firstly, split them to tokens, and then we can find find all the instructions related to branches. Then we can build a safety control flow graph, and then put it to our internal representation. We have 4 levels: function, base blocks, instructions, and each instruction has 1 opcode and several operands. So this is not IR, so it's That's the code structure in our program. And then after that, we'll try to lift the instruction one by one. For each opcode, we will write a set of rules. There is a tool, it's a Python package called LLVM Lite. So our implementation is based on this. But we just mentioned that there's a challenge that because in SAS, there's not enough type information. So before this step, we need to have another step. So type analysis. Firstly, we will build a chain, the definition and usage chain. So when the register is defined, at which point will it used, and then using this chain we can recover the operand types. So let me dive into it a little bit. So firstly, we can for some instructions we can just infer types from opcode like IMAD. The I actually means integer, so we know that R4, R5, R3 are all integers. Also, F8, R2, R7 are floating-point numbers. So this is it. But for this case, move something from move registers from R2 to R6. Here we cannot infer types from opcode. So in the hardware they just move the content from one to another. In this case, we need to infer from context, and so that's why we need to build the definition and usage chains. So if using this chain, if R6 is later used as an integer, then we know here R2 R6 is an integer, and also R2 is also an integer. There's another case. So in the Turing architecture or similar SMs, all the registers, the general purpose registers from R0 to R225 are all 32-bit. But sometimes we also need the 64-bit registers, like when we try to represent an address space. Then two registers can assemble one 64-bit register. Here is another example, also using IMAD. The void is a modifier. This modifier means that so R2 is a 64-bit value. Then here R2 is not R2 itself, it's R3 and R2. R3 is used to represent the higher 32-bit value. And also if this R2 is R6, then it will combine with R7 and R6. So this is interesting. And so more details can be found in our paper. Let's move on. Here's an example. Also IMAD. The C here means constant memory. The C0x0, 0x4. And here's a function, multiply and add. So here is the lifted version. So for the first three instructions, we will load the content from some temporary variables. And so all the register constant memory is stored something is stored in some other variables. And then we will do the multiply and add in the IR. After that, we will store the result to the R3 register. It's also a LLVM IR variable. And okay, so after that, after lifting, we have lifted RR, but we don't know it's correct or not. So we propose a pipeline to check the correctness. We'll do that by differential testing. Firstly, there is a CUDA kernel, and then we will use NVCC to compile it to SAS. And then here, our NVLift will lift it to the lifted version of LLVM IR. In the same time, we will use clone to generate a reference IR. Then we will use LLC, or low-level compiler, to compile it to PTEC, the NDSS, and then we will compile the execution. So this, we will find the same set of inputs, and we will execute them and check if the output is same or not. Okay, here's our implementation and evaluation. Currently, our lifter is working on Turing architecture or SM75, but I think it's easy to apply to other architectures because the core instructions are similar. And currently we support 47 instructions as the figure shows with their modifiers. And then, so as we analysis in the CUDA, the most important CUDA libraries like CUDA-Dn and CUDA-BLAS, like for linear algebra. So we can cover around 90% of instructions. And then to evaluate, we also left 11 CUDA kernels, including some Tian operators like ReLU, convolution, JRU, transformer, and then all of them can be lifted to LLVM and it can also be compiled back to the PTS or SSS. But currently, only 5 of them pass our differential testing phase, and we are still figuring out the bugs. And then we use decompilation as a case study. So we want to show that the lifted IR, our lifter is not only a toy, but it have some usage. And we leverage RecDec, so it's an LLVM-based decompiler. And currently, 7 of the 11 CUDA kernel binaries can be successfully decompiled. These 2 figures are the demos. So the left one is a simple ReLU operator, and the right one is the decompiled version. The function is same, but it's still a little bit complex because I think due to the optimization in the compiling process. Okay, so here's the conclusion. So we built NVLift, so it's end-to-end lifter from SAS to LLVM IR. Then we propose a differential testing-based method to verify the semantic correctness. And we use decompilation as a case study. And so this work is funded by NSF, ONR, and Lockheed Martin. And we welcome any questions and feedback. The code will be released soon. It's not open source now, but maybe in 2 weeks. We are still working on that. Okay, thank you.
Any question? Please state your name and the institution.
Hello, my name is Kevin. I'm from Auburn University. I was wondering, so lifting to the IR is obviously going to be a huge challenge. I was wondering, did you try any other IRs besides LLVM, or what were the challenges there?
No, we currently only target LLVM because I think it will have more benefits because the tools are. So there are many tools than other IRs.
Yeah.
So we're also thinking about lifting to IRs for IDA Pro, for IDA, and also for Jira. Maybe we can also do the decompilation, but the application will be limited. So sure. Currently we only try LLVM IR.
Makes sense. All right, thank you.
Thank you.
So I was about to ask that an obvious use case is decompilation, right? But you chose LLVM-IR. I'm not saying LLVM-IR is not good for decompilation, but you need to do a lot more work after that.
Yeah.
So what kind of use cases do you have in mind for your work?
Maybe do some patches.
Maybe.
Yes. And not think that carefully, and maybe also we can try to find bugs from the CUDA binary by analyzing the LLVM IR, maybe by symbolic execution.
Okay, so like the traditional like bug finding or patching, like this kind of applications.
Yes, there will be some gap, but I think maybe it has some potential.
Cool. Thank you.
Thank you.
So I have a little bit of a redundant question here, but I guess my question is like, what motivated you to use LLVM specifically, and what part of the lifting to the LLVM you found the most difficult, or which challenges did you encounter? What was it the hardest part of this process?
I think it's the time analysis. So just as I mentioned, so because I didn't do this kind of work before, so I need to think very hard to figure out the process of passing the types. And also there are 32-bit numbers, 64 bits, and also there's no documentation. I need to read some very tricky.
I don't blame you, by the way.
Okay, thank you.
We have time for one last question. Okay, so let us thank the speaker again.
Thank you. Thank you.
Next speaker, please. So next speaker is Charles Averill, and he will talk to us about automatic formal fault-tolerant correctness proof for native code.
All right. Hello, everyone. My name is Charles. I am from UT Dallas, and today I'm going to be telling you about some work on formal fault-tolerant correctness proofs. So, can I get a show of hands who's familiar with this image? Oh man, you're in for a treat. Okay, we got one. Okay, who's familiar with Java? Okay, many more. So think of all of the time and money and effort and manpower that has gone into building the Java ecosystem and designing the language and designing the compilers and designing the libraries and making sure it's all safe. And now look at this image and think about the fact that about 20 years ago, somebody showed that you could hijack the entire JVM by writing a very simple program that waits for a single bit flip that allows you to completely, have direct memory access and write arbitrary data to memory. Just waiting for one bit flip, and you can accomplish that by shining a flashlight on the processor. So keep that in mind. All that effort defeated by a flashlight. Now, as software developers, we tend to think that the hardware is supposed to do what we think it does, according to the ISA, where we run an add instruction, it adds two numbers together. But it's not always going to do what we want. And actually, the contract that we have it reads something more like, hardware is going to try to behave correctly if the right conditions are present. And these conditions can be things like the right amount of heat is in the environment, or the right amount of voltage is getting into the processor, or anything like that. And so the hardware designers are developing the chips with these invariants in mind. But as was shown in the previous slide, if you invalidate those invariants, then you can invalidate this contract that we all depend on. And this is a very well-known problem, especially in aerospace and in satellite technology, where you have a chip running in a high radiation environment. So just a regular environment can cause these errors, as well as an adversary who actually wants to take over your machine. And invalidating these invariants can cause a ton of adverse effects: memory corruption, register corruption, pipeline corruption, skipping instructions. There's a whole host of things you can do with this. And of course, there are a bunch of standard approaches for solving this problem. So if you think that the hardware developers should just get better, think again, because it is our responsibility as software engineers for these critical systems to actually handle these problems when hardware can't. And over the past 50 years, we've come up with a ton of solutions for this. You can run code several times, and that will allow you to maybe detect and possibly even correct errors. You can store sensitive regions of memory several times and, again, detect and correct errors. You can do runtime checks of your invariants and the state consistency, or you could implement algorithms several different ways and then run them, and then maybe systemic errors don't happen, and there's fail stops, and you can roll back to safe states, and there's ASLR, and there's a billion ways that software developers have found to handle these specific cases of fault tolerance for whenever the situation calls for it. But a really good question is, how well does any of this work? It works pretty okay. We don't have planes falling out of the sky every day because of cosmic rays, but they don't work as well as they could. There are some issues with each of these approaches. Definitely the big one is complexity. If you store more copies of data and you run code more times and you do voting on the answers and you do error correction, you are making your program more complex. And as everybody in this room should know, if you increase the surface area of your program, you're probably going to end up with more bugs in the long run. More bugs is more, attack surface area, and just a whole host of problems when you make your program more complex. The other big issue is that a lot of these events, or a lot of these methods are probabilistic. So, if I store 2 copies of a buffer, and I say, well, if a bit flip happens in one, I can detect that, that bit is different, so maybe halt the program or crash or whatever, or store 3 and then correct the bit. But that's kind of assuming that the same bit won't flip in both buffers or something. Or it's assuming that, if I have 3 buffers, then I can correct any single bit flip. But what if all 3 get corrupted by some really big memory corruption event? So there's all these assumptions that, this extremely unlikely thing won't happen. But what if it does, right? Then we're all out of luck. But really, the core of the issue here is that these methods that we were hoping would give us some kind of assurance that even in these bad situations, things would go right, they're not giving us any assurance. We wanted assurance, and we don't have assurance. We have really good guesses, which is not really, what we're hoping for, I think. And we already have this thing called formal methods, which is this, host of techniques for giving us formal mathematical guarantees about what code does in different scenarios. But of course, we don't have a solution. I'm giving a talk here, so obviously we don't have a solution yet. But how can we get these assurances, these mathematical guarantees for these fault-capable environments? And that's what I am presenting today. So I'm introducing LAPSE, Logic for Analyzing Program Skip Effects, which I think is very clever, which is a framework for developing machine-checked, fault-tolerant proofs of correctness. So that machine-checked is really the key development here. So it enables you to construct this proof of correctness, assuming some kind of fault model that describes the environment your code is running in. So this could be the number of instruction skips that could happen throughout the run of a program, or the amount of memory that could be corrupted at any given time. And with this framework, you can get these actual mathematical guarantees that your code is correct, or it's safe, or it's well-formed, or it has some property that you want, any property that you want, within your given fault model. Now, of course, this is not easy. Everyone in the binary analysis research workshop knows that analyzing binary code is tough, and there are a ton of issues. With any formal or even semi-formal approach, you of course are going to run into the state space explosion problem, where so many things could happen that all of a sudden you have 2 to the 100 different states that your program could be in, and how are you supposed to analyze that? And of course, again, all the problems with binary analysis are here. You don't have decidable disassembly. You don't have decidable CFG recovery. You have to reason about binary arithmetic and pointer arithmetic, and maybe you need an SMT solver, and maybe you have to model hardware interaction. There's all these problems that we all know and love. And of course, how do you even express the idea of a fault in your normal binary analysis tool? What modeling decisions do you have to make? How expressive can you make your propositions about how the program is behaving? How do you handle non-determinism? Because these attacks can be non-deterministic, especially if you're thinking about radiation errors, right? There's just so many things you have to worry about. And of course, this is not the first time somebody's had this thought that we should apply formal methods to this problem. We have several approaches that hit different points in in this problem. And so PVS is a very famous, very old system developed by NASA 30-ish years ago, and they use it to verify all their critical systems, and it's still kicking. We have projects that try to verify binary programs, or they try to make binary programs fault tolerant against things like instruction skips by rewriting them and then formally verifying that the rewriting actually does make them fault tolerant and preserve semantics and whatever. You can verify, specific implementations of algorithms like AES to make sure that fault injection attacks, won't hijack anything. But each of these has pretty significant limitations. For example, PVS, you can't lift, or you can't write a proof about a C program in PVS directly. You have to design your program in PVS and then extract it to somewhere else. So if you have legacy code, you're kind of out of luck. The rewriter project really only model checks the rewriter rules. It doesn't actually do any verification of the tool itself. So maybe the tool is written wrong, or there's a bug, or now you've got false confidence, which is honestly even worse than not having any confidence, right? And this AES implementation, it is formally verified, but the proof actually assumes that there are no control flow attacks, and then just model checks those scenarios in which a control flow attack occurs to see if anything doesn't happen. So all of these attempts have pretty significant drawbacks, and then they don't even handle the problem of like state space explosion, or like how do you do symbolic execution soundly so that you traverse every path, and how do you scale this? How do you make it general to other ISAs? So many problems here. We want to traverse every single path of the control flow graph to make sure that every single possibility is covered. We need some kind of ISA semantics that supports non-determinism, so you can handle undefined behavior and hardware interactions and model these faults correctly. You need some really flexible intermediate representation to encode fault behaviors. So that way you're not rewriting your symbolic execution algorithm every time you want to model a new fault. And the really key thing is that you want machine-checked proofs at every step. This whole thing was we want more assurance, so we want machine-checked proofs every step of the way, no gaps. And then you get bonus points if you can automate your proofs, or if you can handle multiple ISAs, or if you can scale up to different fault models. It's, that's just bonus. So a framework with all of these properties seems like it would be really hard to write, and it would be a whole lot of work, and that's what we did. So LAPSE is built in ROC, the ROC proof system, on the Piccaninny binary analysis framework, which was developed for DARPA vSpells. And so this allows you to write arbitrary or proofs of arbitrary properties of arbitrary code. It's ISA generic, and we've instantiated it to RISC-V just for the demonstration. It's designed with instruction skips in mind, hence the name, but it is extensible to any fault that could be simulated with a near Turing complete language. You have declarative fault models, so it is plainly obvious what your proof covers and what it does not cover. It's automation capable. I'm going to talk about this in a second. And then we have a native embedding of non-determinism, so it's very effortless to represent the possibility that a fault could happen or couldn't happen. And so what does it actually look like to use this system? Well, the first step is to have a proof of a regular correctness proof for a fault-free environment, which I know we're probably not happy about that. But the story here isn't that this is easier than regular verification, but that it's not much harder, as I'll mention in a second. We provide a number of fault models for different kinds of faults, memory corruption, instruction skips, that a user can select to build the machinery that allows them to write their fault tolerance proofs. You wrap the lifted program in an IL modification function that is going to inject a fault simulation at every instruction, and I'll show an example of that on the next slide. And then you take your initial correctness proof and you perform some minor syntactic adjustments and wrap up all your proof logic into one tactic that you can dispatch as the symbolic execution traverses the control flow graph and hits various invariant points. So the idea here is that once you've written your initial correctness proof, generating a fault-tolerant proof is essentially automatic. as long as you can copy and paste the tactics that you use to write your initial proof. So we have an example of a fault model here and one of these simulation injection functions. Inject skips basically says if an instruction skip is possible, then do nothing but modify these virtual registers for timing faults and whatnot. Otherwise, actually execute the instruction. So when you hit the proof, when you hit the step in the proof, it's going to split into two branches because we have this unknown construct that splits our control flow graph in two. And then we have this fault model here for non-consecutive skips, which just shows that you can have n faults and there has to be one non-faulted instruction in between them. So that represents non-consecutive skips. And we have some examples that we've proved fault tolerant with this framework. I pulled out a few functions from OpenSSL and BareSSL. I performed this dual modular redundancy transformation of them, which essentially means run all of the instructions twice after performing an idempotency transformation. And these proofs were not that hard. These time figures include the time to write the initial correctness proof and the fault-tolerant one. And we can see, constant time mem compare took me about an hour to write both proofs. Conditional mem copy only took me about 15 minutes. That was a really pleasant one. And then we have this very tough triple modular redundant password checker. There's an interesting story here that I'll talk about, I guess, if somebody comes up to me later. But this required some interprocedural analysis, which was very tough. It ended up being like a 600-line proof. Took me a few days. But it does use an almost unmodified crypto mem compare. So this is kind of thinking about the situation in which you're calling into some library that you don't support. And we were able to prove that all these functions are correct. The transformations of these functions are correct, even if instructions are skipped. So we are still working on this, obviously. We'd like to continue building up our set of fault models. We'd like to better support memory corruption, and we'd like to, perform some survey of all the different kinds of faults out there, and write better injection functions, and write more proofs for real-time systems and aerospace applications. There's a whole lot of work that can start from here, and of course we want to make it more automatable because who doesn't like automation? So that's my talk, and thank you so much for listening. And if there's any questions, I'll take them now.
Thank you. Any question?
Can you tell us a little more about how long it took to write the initial proofs and how much more work it was to write the fault-tolerant ones?
Yeah, so crypto mem compare and the conditional mem copy were the first two proofs that I wrote. I actually did not even know what the fault tolerance proofs would look like, but I was extremely pleased that, I told you that with this non-deterministic branching at each instruction, you end up with this big tree of proof states, but they all end up at the same invariant point. And so it was very nice that on each branch I could just say, step until you hit an invariant, and then, oh look, I already solved the invariant for the regular correctness proof, copy and paste. So for crypto mem compare, it probably took me 40 minutes to write the normal proof and then 20 minutes to write the fault tolerance proof, and that was the first one I did. And once I realized that you could do that, conditional mem copy was probably 10 minutes for the initial proof and 5 for the fault tolerant one. The TMR program, that was really tough. This was actually the first time I did function calls in Picana, which we've only recently added support for. And so that took, probably a day and a half to figure out how the regular proof would work, and another day and a half to modify the fault tolerance proof, because it was just such a different experience. So, yeah.
Thanks. So maybe just a quick one. How do you plan on automating the transition?
Yeah, so with TMR, we found that there were a number of patterns on how callers and callees interact when the callee could fault or could not fault. And so generalizing those behaviors is into, automation tactics, that is the way forward for making interprocedural fault tolerance analysis better.
Hi, Samuel Giroux, MIT Lincoln Laboratory. First, really, really cool work.
Thank you.
I may have an operating system we built around SL4 targeting satellites for which this is wildly appropriate. I guess one of the questions that I have is, you talk a little bit about the fault model or the ability, like how extensible is what you've got for broader fault models? Because like skip instructions and stuff are great, but radiation in particular has really broad potential issues.
Yeah, this is a great question. The immediate next step that we're looking at is the decoding pipeline corruptions. So arbitrary instruction corruption is definitely our next target. But the answer is that we can, our IL is, I called it near Turing complete. We have unbounded finite loops, but not infinite loops. That's the only difference. So anything you can represent in a standard IL that doesn't have infinite loops, you can represent in this framework. Yeah.
Interesting. Cool. A second question, if I may. SCL4 seems like an obvious choice to apply for something like this. How close are you to beginning feasibility on something, even that size?
Yeah, so like I said about interprocedural analysis, we have some work to do to actually generalize, the work on this TMR proof to make sure that we actually can scale this up. There is a pretty clear pattern that's available there. So we're not close, but we are working on it. And, over the next year, this is going to be probably one of the primary things I'm spending my time on. So, I don't know, a while.
Sure. Super cool work again. Thank you.
Thank you so much.
Okay, we don't have time, but I still ask a question because I am the chair. Could you tell us a little bit about this example? Do they natively have protection, or do you add protection? And if yes, especially the two first one, because
Yeah, so the first two, I pulled the C code straight out of OpenSSL and BareSSL, compiled with optimizations, and then manually performed this DMR transformation because I couldn't find a rewriter to do it. But essentially, you have to make each instruction idempotent, so if you run it one time, it has the same effect as running a billion times or whatever. Then just duplicate every instruction sequence. So that was the transformation I performed, but I didn't change the logic of the program at all.
Okay, and it seems to be that you are protecting against an arbitrary number of skip injection fault. Is it the case? Because usually what I see in smart card or this kind of thing, people say, okay, I can protect against 1 injection, 2, 3, 4, but not an arbitrary number.
Yeah, so these proofs and the automation I've written for them do indeed support arbitrary numbers of non-consecutive skips. There is a scaling issue, and I've ended up crashing my machine a few times when I try to bump the number up. I don't have the exact figure on hand, but I can find it later.
Okay, thank you. Thanks again.
Thanks.
Next speaker, please.
So I see the slides on this screen, but not that screen. Oh, there we go.
So next talk is about Dilipa, making micropatches via edits to lifted C.
All right, so good morning, everybody. My name is Ben Karel. My coworkers and I, a few years ago at Aarno Labs, created some tooling to make it easier to make small changes to binaries. So we targeted this towards a very particular scenario. We want to take what we call generalist engineers, which for us means people who know C, but not necessarily assembly, and have them take unmaintained programs, by which we mean programs that they don't have the source code for, and in particular, you assume nobody has the source code for anymore, because let's say the company who owned the source code went out of business. And we want them to be able to create small patches to these binaries. And by small, I mean small at the binary level, not necessarily the source level. So so for this goal, we're sort of bringing two big ideas to proposals. So the first is that we want a workflow in which these engineers modify binaries by making interactive edits to lifted C source code representing the binary semantics. And the second is that the patching process involving that lifted C code should not itself be trusted. Instead, we should derive assurance in the patched binary from ground truth results, that is, static analysis of the patched binary itself relative to the original binary, characterize the semantic impact of the patch that way. I want to point out that both of these ideas really hinge on the assumption that we have small patches being made. If you start talking about or trying to support arbitrarily large patches, changes to the binary semantics, both of these ideas kind of break down. But if you do this restriction to micropatches, you get, I think, a much more tractable problem. So our paper really focuses on just point one here, just sort of easier to write a paper about this part of it. But we do think that the sort of assurance aspect of it is also very important. So this is the overall flow of our patching process. We start with the original binary in the upper right side. We feed that into an existing open source static analyzer called CodeHawk, which takes the binary and decompiles it, producing lifted C abstract syntax trees. We present those ASTs to the user, allow them to make edits to that serialized code. We extract AST differences from the edits that they've made, and then convert those AST diffs into binary level edits. So let's look at an example of this in action. So here's just a little bit of C source code. It's a very small, simple function. And this is what it looks like in thumb2 assembly. And we produce sort of multiple layers or levels of AST. At the sort of lowest level, we get C that is basically just a transliteration of binary semantics into C syntax. I'm guessing you're probably very familiar with this style of decompilation. The coloring here is just to sort of indicate or suggest that there are links between, sort of obvious links between the C syntax and the binary semantics, the individual instructions and all that. So we also have a higher level lifted AST that, to the greatest extent possible, elides sort of irrelevant or unnecessary information from the binary level and presents something much closer to source code. So in the previous slide, the sort of detailed AST, if this function had control flow, the detailed AST would have goto statements, and the lifted AST would have ifs and while loops and things like that. I am taking one small liberty here, which is that name and type, information about global names and type fields of structs and things like that is an input to our system, not an output. So that's sort of an interesting research area. It's just not what we're doing. That can come from several places, but here in this example, we do sort of assume that that's been provided. I'm showing the serialized form of these ASTs, but they are internally represented in a much richer structure. And this richer structure sort of gives us the surface area on which to hang the provenance metadata that allows us to connect all these sort of AST levels and elements from the AST back to the original binary. So let's say the user modifies one particular expression here, sub-expression. In the very last function call, they change the constant from constant 4 to constant 32. In this case, we would sort of do a pairwise comparison of these ASTs and find that, okay, the first two function calls are identical in the ASTs, and in the last one, it's just the last one, the last argument that differs. And sort of using the provenance metadata embedded in the AST, we would see that, okay, this constant is being assigned into a particular register at a particular instruction location, and we had synthesized what we call a patch description fragment, which is basically just a small snippet of C source code that reflects the edit that was made to the AST, along with some extra metadata that allows that to be sort of applied to the binary. So here the compilation of sort of the statement R2 equals 32 into thumb2 assembly would be a sort of a 2-byte instruction. And in fact, if you sort of look at the existing binary, one of those bytes is unchanged from the original binary. So the result is that as a result of making this small change to the C syntax, you end up with a 1-byte patch to the underlying binary. So this is obviously a sort of small and trivial example, but we have found that these surgical micropatches do come up in practice. Right, so I'll slice and dice this diagram a little bit and talk about some of the individual elements, a few details from each piece. So CodeHawk is, as I said, an existing static analyzer. The core functionality it provides is sound inference of program invariants. So it does this for C source code and Java. It also does it for a small handful of binary ISAs. It's based on the theory of abstract interpretation, and we extended it to basically turned it into a decompiler that can produce these CASTs that we need. We looked into several other options for if things like Ghidra or Binary Ninja could do this job, since they already have existing decompilers. And what we found is that for our purposes, so the main two elements that were missing or challenges that we didn't really see exactly how to overcome, first is that in order to sort of do this workflow, you need to have parsable C, and in particular, you need to have type compliant C. So it's not just enough to have the C syntax, but in order to do sort of general parsing of C code, you need to have types work out. We do parsing with George Nekula's CIL toolchain and sort of infrastructure, and basically with CIL, if you have a type error in your C code, you don't get an AST back. So that ends up being one challenge that CodeHawk seems to be so far better than alternatives. Another is that the existing decompilers tend to be oriented towards interactive usage, and CodeHawk sort of originated as a platform for guaranteeing the absence of undefined behavior in C code, and it was sort of an offline, batch sort of workflow rather than an interactive one. So the sound program invariants that it infers, we make that available in the generated ASTs so that you can have sort of a mapping of high-level expressions that appear in different registers, and that's difficult to do in an interactive tool. So the others had different constraints, and so just weren't quite as well suited. Right, so one sort of a requirement of this workflow for the next step is that if there are no edits you made at the source level, the ASTs need to match. So in some sense, this needs to be, CodeHawk needs to provide ASTs in canonical form. That ends up being finicky. It's not impossible, but it is a non-trivial engineering challenge to make sure that the ASTs you provide always sort of have this round-trip clean property. But once you do have that property of being round-trip clean, then that enables you to infer that from any difference in the AST, that difference came from an edit that the user made. the AST differencing process itself is fairly straightforward. There are sorted wrinkles in the details, but we basically identify divergences in statements and expressions and do case analysis on what we find. We have sort of both special case handling and generic fallbacks in order to map the sets of edits we care about into snippets of C code. There are edits that we sort of don't aim to support because things where a small change at the source level would be an overly large impact at the binary level. So for example, changing the type of a global from int to float is going to have very wide-ranging consequences. And since we're really focused on small patches for patching security vulnerabilities, that's sort of not something we're expecting to be needed. And we call this the front end. Basically, everything that goes from ASTs to these patch specifications, this sort of snippets of C code, we call the front end. This is derived from the traditional compiler split of front end and back end. So for us, the back end is basically the component that takes the patch specifications and applies them to the patched binary. For this, we rely on Clang. We sort of do some light source-to-source rewriting on the code that the user provides, and pass it to Clang in sort of a specialized harness or framework that allows us to extract the compiled bytes for just the piece of code that we're interested in without having interference from function preludes and things like that. So we try to generate sort of direct overwrites when possible in order to sort of take existing instructions and replace them directly. If that doesn't work, for example, because the user changed a small expression into a big one or they inserted a statement, we also have automatic fallback to trampolines, which allow us to handle sort of various more complicated code sequences than you could get otherwise. And we also have sort of a handful of techniques for creating additional space in ELF binaries. So far, we've only been looking at ELF. These techniques have worked sort of well enough for our purposes, but we can't claim that they work for in every situation. And then, as I mentioned earlier, one of our key ideas is that the patches should be treated as unreliable, and we should try to gain assurance in the patched binary by subjecting it to static analysis. So Codehawk can peek through, in some sense, the inserted trampolines and associated control flow in order to, as much as possible, characterize the semantic impact of the inserted code without interference from the implementation details of trampolines. Our implementation has recently been open sourced. It's a little bit iceberg shaped in that sort of above the waterline, there's 10,000 lines of Python code that sort of orchestrates the passing code to Clang and doing this AST differencing. And then below the waterline, there's another 30,000 lines of Python for producing these ASTs, and then the Codehawk analysis engine is 300,000 lines of OCaml. Our core focus was support for 32-bit ARM and Thumb, but we did prototype support for some other ISAs as well. Our paper doesn't mention a GUI, but we did build one, and it's pretty slick. I do encourage you to search for Aarno Labs on YouTube, and we have some short demo videos that are, I think, pretty nifty. Of course, nothing is perfect. Not everything is sunshine and rainbows. So, as I mentioned, we don't aim to support every possible edit. We really are trying to sort of focus on the subset of edits that we found to be useful and necessary for the security patches we've encountered. We if you have a stripped binary and you have no means of producing name or type information, labels for fields and things like that, obviously that's going to be more challenging than if you have that information provided either from debug metadata or from other techniques. If you have headers but not source code, that's a lot nicer. As our paper goes into, we don't provide full support for optimized binaries. By which I mean there are situations in which certain patches to certain kinds of optimized code might go astray due to the heuristics we use for doing the mapping from C AST edits back down to the binary. And one interesting thing that I sort of hadn't anticipated going into this is that error reporting turns out to be pretty difficult when one of your assumptions is that your users don't have the vocabulary or sort of concepts to understand the errors that can occur at the layers below them. So this would be a lot easier to sort of explain what's going wrong and guide users to a better alternative if we could assume that they had a little bit more knowledge. But in any case, I'll sort of do the weak version of this claim, which is that we believe that some useful micropatches can be created for some real-world binaries via this workflow of making edits to lifted C source code. The restriction to micropatches makes this tractable, and we are actively extending this work with support from ARPA-H to apply to legacy medical devices. If you're sort of interested in chatting more, I'd love to hear from you. So that's my talk.
Thank you. Any question? Please go to the mic.
I know you said you don't want to go into too much complexity for your patches, but I was wondering if you thought about integrating this approach with Coccinelle. If you're not familiar, Coccinelle is that semantic patch approach from, I believe it's from INRIA, right? The Linux kernel has been using that for a long time. There's actually a bunch of recipes in one of those folders in the source tree. And it's basically semantic patches that are generic, that apply to different situations. You could think of those as abstract patches, so to speak.
Yeah, I've looked at Coccinelle in the past. My recollection, maybe I'm misremembering what it was that they're sort of interested in sort of large-scale, source-level transformations. So, and maybe we should chat offline, but I guess I'm confused about sort of where you would see the sort of crossover between the two projects.
Oh, okay. So they're not necessarily those semantic patches can be very small and precise. They don't necessarily have a large scope, but they're generic, so you can reapply them in different situations, which is kind of interesting. So you can essentially symbolically apply those patches, if that makes sense.
Okay. Yeah. So I think one interesting area would be sort of helping human users find likely candidates for where in the source code they might want to be patching. So yeah, and maybe not doing the patch itself, but sort of ranking or suggesting, if you sort of have an unfamiliar binary that you don't know what's going on with it. I could imagine that sort of having some repository of suspicious patterns might be useful.
I'd love to chat more about this offline.
Okay.
And I see you also integrate OCaml, good choice by the way, and Python. And I was curious if you have any tricks here for like making them interoperable, or do they work in separate, processes?
For historical reasons, the OCaml and Python sides mostly communicate via XML, but it's a very sort of it's almost like a semi-binary XML. Like I said, so CodeHawk is nearing its 20th anniversary, I think. So obviously, like the serialization landscape in the early 2000s was just much different than it is now. And it's one of these things that it ain't broke, so we haven't fixed it.
Thank you.
Hi, great talk. I'm Luke from Carnegie Mellon University. One of the things that kind of excited me about this work is you have essentially recompilation of decompiled code, where you can get, as you said, if you make no modifications, you should get byte equivalence. You should get the exact same binary byte for byte. That's really cool, and that's something that you don't get in a lot of commercial decompilers. So if you use even IDA Pro decompiler or Geezer decompiler, you often can't recompile these things. And if you can, you're going to get a lack of byte equivalence. So I think part of this has to do with the fact that you do this, do a lot of work to keep the ASTs consistent. That's my intuition. But can you comment more on how this is the case and how this could be applied to other commercial decompilers to make it easier to recompile with byte equivalence, which is super cool.
Right. So, I mean, I think a fairly important aspect of what we're doing is that we try to avoid recompilation as much as possible. So, my understanding of the sort of related work in the literature is that the sort of standard alternative is like function level recompilation, where if a function changes, you sort of pass the whole function to the C compiler and just use that as your replacement. And it's like, from what I've seen in the literature, that has like a 95% success rate, which is on the one hand pretty good, and on the other hand, well, what about that other 5%? And we have sort of different trade-offs because we can have a fair number of errors in the lifting, and it doesn't matter as long as those errors aren't where the patch needs to go. Right? So you can have a function that is 80% wrong, and if the patch you need to make is in the 20%, you're fine. Or it can be 98% correct, and if you try to recompile it, that 2% will make it not work. But as long as you're in the 98% that's not wrong, in terms of your patch and the metadata, then our technique would succeed. I think the trade-off is that, like I said, for optimized binaries, we have a much higher burden of sort of disentangling sort of what the binary is currently and what it would have been if we'd made the source change. Like if the compiler had seen the changed source, how would that binary have been different to begin with? And when you're doing function level recompilation, that isn't something you need to worry about because you're just replacing the entire thing wholesale.
Yeah.
So I think it's an interesting thing that the function abstraction ends up being pretty powerful, sort of both sides. Yeah.
Thank you.
Okay, so let us thank the speaker.
Yeah. Thank you very much.
Next speaker, please. So next talk is about BPA-X, an architecture-agnostic block-based post-to analysis for strip binaries.
Okay, hello everyone. I'm Bokai Zhang. I'm from Penn State University. Today I represent BPA-X, architecture-agnostic block-based point-to analysis for stripped binaries. A major challenge in building CFG or control flow graph for stripped binaries is that commercial off-the-shelf binaries usually have no symbol tables or source-level type information. When dealing with individual cores, like core RAX, reconstructing the accurate CFG is very challenging without these symbols and types. So the goal of our research is to build a sound and scalable static analysis for individual cores. there's some pure work in this topic to solve the problem of missing types in strip binaries. Some work like TypeForge, Tiger, it can recover types, recover like very rich, like close to the, not working. Okay. Yeah, thank you. Some work like TypeForge, Tiger, they can recover some source level types like a struct, array, or like nested struct. But these types are insufficient to determine the indirect call targets. We have found mainly conflicting types between the caller and the function signature of the callee. And recently, some machine learning approaches like callee, 10call, they trying to resolve the indirect call targets, but their results are not sound since they use probabilistic embedding matching to find which targets is to find the targets of indirect calls. Some static analysis tools are scalable but not sound, and one promising work is both sound and scalable is a block-based value set analysis, but it relies on 32-bit x86 instructions. So our contribution is that we generalize BPA or block-based point analysis to be architecture independent on VexIR. First, let me briefly introduce this memory block model. It is proposed in BPA. The memory block model is partitioning memory regions like local, global, heap regions into memory blocks. Let's look at this diagram. So it maps struct V1 to memory block 1. It mapped like int array V2 to memory block 2. It maps V3 and V4 to memory block 3. The key assumption in memory block model is that all pointer arithmetic should be restricted within the same memory block. For example, the pointer arithmetic starting from memory block 2 should be only allowed within the same memory block. It's not allowed to point to another memory block like memory block 3. And it can guarantee the soundness as we are tracking the values in the memory block level instead of on byte level or word level. And you can see in this memory block model, it maps both V3 and V4 into memory block 3, and that's very common as we are trying to build this memory block in a very sufficiently coarse-grained way, so that it's more scalable than the traditional like value set analysis, and in this way we will not affect the soundness. It only affects the precision. In the BPA, it has some heuristics on x86 instructions, while in the BPA-X we extend these heuristics or modify these heuristics on VexIR semantics. This is a workflow of the BPA-X. It starts from a binary and using Anger, like CFG fast and VexIR lifting to data log facts. In our implementation, we use data log souffle to implement this value set analysis. So it's all based on the data log facts. And then it's partition the memory into memory blocks, and also perform register SSA transformation. So we got more facts about instructions on memory blocks and index registers. Then these facts are fed into the fixed point iteration. In this fixed point iteration, it has 3 components. One is value set relations, one is CFG relations, one is region definitions relations. For the sake of time, I will skip this the first part, like Anger analysis and input pre-processing. I think many of you are familiar with Anger and their like IR, like VexIR. So I will start with this memory block partition. So for memory block partition, we have 3 types of memory blocks: local, global, and heap. For local memory blocks, they are usually like function arguments, and arguments pushed on a stack for callees when it's like x86 programs, and some local variables or some temporary variables assigned by the or created by the compiler, etc. We track the offsets of temporary registers relative to the stack pointer value at the beginning of each function. But these offsets, not all offsets are memory block boundaries. So we use some rules to determine which offsets are memory block boundaries and which offsets are not. So for example, for positive offsets, there are always function arguments as there are always function arguments, and these offsets are memory block boundaries. We also perform calling convention analysis for arguments pushed on a stack, because in 32-bit x86, all arguments are pushed on a stack, and in 64-bit, it's push arguments on stack when there's too many arguments. And also, we perform a size inference for arrays by detecting loops. This is very important because we do not want to partition the memory into very fine-grained way. We do not want to break the soundness of this value set analysis. For example, let's look at this code. It has an array of, as an int array, v2 have 5 elements. Yeah, five elements, and in the for loop, it has access to each element, and also it has access to with direct index, like index 1, to this array. In the assembly, you can see starting from this push and move. This is a prolog in the function. Right now, the EBP, the register EBP should have stack offset -8 because it has a push. Word size is 8 bytes. And then it starts from this loop. We can see this at line 1183. It stores the EDX to this memory location. And this location has offset -28 plus 4 times REX. Because this is in a loop, and we can detect that this is, and this this array has a boundary between this array has a boundary like from -28 to -14. So no memory block boundary should locate within this interval. And then out of this loop, we have a direct access to this first or the index 1 element. And you can see this offset have -24, but because -24 is within this this interval of this array, so it cannot be a memory block boundary. So that's how we prevent the oversplitting the memory into in a way of to ensure the soundness of the memory block partitioning. Also, we did this we did value tracking for global memory, like the data regions, our data and BSS. Also, for heap memory blocks, we assign one memory block for each allocation site. For example, like malloc, invocation of malloc library functions. And this is a balance between the precision and the soundness, precision and the scalability. Next, we look into this register SSA transformation. In BPA-X, there are 2 types of registers. One is VexIR temporary registers. One is machine registers, like RX, RSP. For VexIR temporary registers, they are local and they are static and single assigned. So it's not necessary to assign SSA format into these types of registers. Next, for the machine registers, like RX, SP, we assign each write with a unique ID, and we perform reaching definition analysis instead of like explicit 5 function. The reason is that because our framework, our BPA-X is implemented with souffle, data log souffle, and it's very hard or almost impossible to remove or modify existing values in the value sets. We can only add the value into the existing value sets. So like it's monotonically increasing. And if we use like 5 functions, we have to dynamically modify this read or like modify the SSE index for the read of registers. So we perform the reaching definition analysis with the fixed point iteration. And for Collie-saved and color-saved registers, we treat them differently because for Collie-saved registers, their values are not affected by colors or collies. They are their values remain the same across after calling the collies. So for Collie-saved registers, we only perform 1 round of reaching definition analysis. For color-saved registers like RAX, RCX, they are used for like return or like passing arguments. We perform the reaching definition in the fixed point iteration. Next, let's look at this fixed point iteration. So they have 3 components: value sets, CFG updates, and reaching definitions. For value sets, it contains the memory block. It contains mappings from memory blocks, index registers, and temporary registers to memory blocks and address-taking functions. For CFG updates, why it should be in the fixed point iteration is that when we have more values in the value set, it can possibly affect the CFG because in the indirect call, it's call RAX or call a temporary register. And the value of this in this register can affect the target of the indirect call. So it can affect this CFG. So in the CFG update, we dynamically add more targets, add more edges based on this value set change. And for the reaching definitions, because the CFG have more edges, for each read, it possibly have more reachable definitions for these registers or for memory blocks. And this reaching definition analysis can also affect these value set relations because more definitions are reachable and this value set can increase. So all of these 3 components are correlated with each other. So that's why we need this fixed point iteration to get the accurate CFG, accurate value sets. Let's go to the evaluation. The first question is that how well is memory block partition in BPA-X based on VexIR? We use the ground truth of dwarf debug information. It has some source level variable information. It's not perfect because our memory block model has assumption on pointer arithmetic, and we assume that there's no pointer arithmetic between different variables, different source level variables. So now I think that's the most appropriate ground truth we choose. Yeah, it's the dwarf debug information, and we test it on the spec benchmark and the 5 other real-world binaries. In this table, wrong memory block boundaries means it has a memory block boundary within the source level variable, so it oversplits the memory, so it can lead to possible unsound when resolving indirect calls. For missed memory block boundary, it can only affect the precision as it's like we are combining multiple variables into one giant memory block. We can see in these tables we have better or similar run rate and miss rate except O1. Have a higher miss rate in O1 because for for O0, higher miss rate for O0, because for O0 there are mainly like push and pop instructions, and our like conservative VexIR semantics is it's too conservative, and it can miss some memory block boundaries. Next question is, what are the precision and recall rates of indirect call analysis? We use the profiling-based indirect call ground truths, and we have checked the results on the spec benchmark and 5 other real-world binaries. We have confirmed that it's a 100% recall rate. And this figure shows the precision. You can see for the most programs, it only shows its precision for large benchmarks. You can see it has similar or better precision compared to the baseline BPA, except O0. As I just discussed that O0 we are too conservative, so the precision is worse than the BPA-X, than the BPA, the baseline BPA. And there are more details in the paper. Then how scalable is BPA-X? We measure the time and the memory usage from end to end. We found 13% reduction in time and 25% reduction in memory. And also there are more details in the paper. For the future work, we want to improve or replace the memory block partition heuristics, because these heuristics are human written rules, and it possibly have some wrong memory block boundaries, and it can lead to some unsound case. And then we also want to evaluate on more programs, as right now we only evaluate on the spec benchmark and other five real-world programs. And for downstream implications, we expect that this result can be useful in control flow integrity enforcement and software debloating, because it requires the sound like CFG. And that's my presentation. And, thank you for your time.
Thank you. Any question?
I think it's very interesting that you mentioned that the precision is lower on O0 because of pushes and pops. So I wonder why you choose to use a lower level IR instead of a higher level IR, where pushes and pops can be eliminated in a higher level IR, right? By saying a higher level IR, I'm referring to some IRs that are closer to C. For example, Anger has AO. That we do all of this stack variable identification and useless write elimination for you already. So why using a lower level IR instead?
I think we are using the VexIR from the Anger. It's it's higher level than the x86 instructions. Like original BPA is using some heuristics on x86 instructions, and our heuristics is based on the VexIR semantics. So it has no push and pop instructions. It only has some store and load to the memory and from memory. So we might miss some memory blocks that caused by the push and pop. That's why for O0, without any automation, we have our heuristics are more conservative, and we can miss some memory blocks. So that's why we have a higher miss rate for O0. Yeah. Does that answer the question?
I think I will have to debug your code and see why this is the case, because I at least in my experience, in modern binary analysis, especially when developing decompilation techniques, figuring out how stack variables change in a single function is the very first thing that you do, and you cannot do it wrong. So if we attribute things to like pushes and pops, this just seems a little weird. But obviously, I don't know your exact implementation, so I think taking a look will be useful. Thank you.
Maybe one last question. You were talking about your assumption. So when I see sound binary program analysis, usually I don't believe it. So I will push you a little bit. So you were mentioning this assumption of separation between the blocks, which is pretty standard. But I mean, are you able to handle any nasty trick you can have on binary code, like self-modification or these kind of things? Or can you detect them, or can you just suppose they are not there? Or?
Yeah, that's one of our future work, and I think using sound indirect calls, like sound CFG, is it can be useful in some scenarios, like we require the soundness because we do not want to break the execution of the program. So that's our field work. Yeah.
Okay. So let us thank the speaker again. So now is the last talk of the session. And the talk is about does representation matter, evaluating intermediate representation for LLM-based binary decompilation.
Okay, thanks for presenting. I'm Tomás Pelayo from the University of Zaragoza. Today we are going to talk about the decompilation and the LLMs. First of all, what is a compilation and decompilation? The first thing is that the compilation is the process of transforming human-readable source code into binary to execute in the machines. And also, the compilation is the reverse process in which you have the binary, and you need to know, you want to recover the original source code. Because of the compilation, you will lose some valuable information, such as variable names, types, structures, and comments that you don't have it in the binary, and it will be very important for the compilation, but you don't have it. Modern decompilators use intermediate representations to enhance their performance. In the case of the binary ninja, which is the tool that we have used in this work, have three hierarchical intermediate representation, which is the lower level, the medium level, and the high level. We can see here a quick example of the max function, in which we can see the assembly, which is not part from the binaries ninja intermediate representation, and then we can see the low level, the medium level, and the high level. In the case of the lower level, it removes the architectural specific details, as we can see. After that, in the medium level, it adds data flow analysis. And in the high-level representation, we can see the most abstract, that we can see that it only takes one line to present the function. Using LLMs, we can see that LLMs have shown strong results in code-related works. Because of that, too many people, too many researchers have used the LLMs and for the decompilation. Because of that, there are a lot of works that use the LLMs for decompilation. But in all of these cases, they use only the LLM as a direct translator from the assembly to the original source code. They don't use the higher abstraction levels that the modern decompilations give you. Because of that, we did this work. First of all, we have to introduce our experimental setup in which we use 2 large models, which are GPT-4.1 and Sonnet-4, and 3 small models, 2 from OpenAI and 1 from Cloud family. Because of that, we have two sizes of models, the large and the smallers. And also we have 2 families of models, which are the OpenAIs and the Anthropic. For the dataset, we use Xavenge, which is the only dataset which gives us unit test to test if the compiled code it really does the same, to check the functional validity. To use the functions that we use in this work, we use it and stratified sampling to avoid the dataset being dominated by trivial functions. In this case, we use it the cyclomatic complexity to make this sampling. Also, we propose an evaluation pipeline in which we have 5 steps. The first one, we complete the function lonely. After that, we get all the intermediate representation from Binary Ninja. The third one is to execute the compilation with the 5 LLMs 10 times to have an statistical validity, and because of the statistical behavior of the LLMs, probably will have some changes from one execution to another one. After this step, we recompile all the code. In this case, we will have all of the compilation errors, and the last one, all the code that has been compiled successfully. We will test it against the unit test that Xavenge provides us. Here we can see the results, which are that for large models we can't see any difference between all of the representations, but for the smaller ones, benefits a lot using the high representations. We can see that for OpenAI smaller models, we can see that for all of the first 3 intermediate representations, the performance is very low, but for the case of the high-level representation, we can achieve a little less than 50% of accuracy. After that, we will see, okay, the overall performance is okay, but we will see what happens when we test and we present all the results, but differentiating by cyclomatic complexity. In this sense, we can see the performance divided and the evolution through the cyclomatic complexity, but we can see that there is a decrease as the complexity rise, but it is not clearly. It is have peaks and drops. There are, sorry, they are very clearly here. So we said we are using really the best performance predictor for the LLMs in the task of the compilation. So to this, we choose to use another metric, which is the half-step metrics, that in the case of the half metrics, they use the operators and operands to say and to propose the code complexity. For that, we use the volume, which is the size of the program, also the difficulty, that it is how hard is to understand all the code for a human, and also we use the effort, that it is basically the mental effort that you need in terms of time and heart to understand all the code. we present here the GPT-4.1 results, which are, we can see that in the case of cyclomatic complexity, we can see all the drops and whatever, but for the other metrics, we can see that the decrease is smoother. And this allows us to think that probably the Halstead metrics are the better predictors for the compiling code complexity for the LLMs. Also, we can see that large models can degrade slowly, but the smaller ones, as we can show in these cases, decrease faster. Just as concluding remarks, are the higher choice matters, especially for the smaller models. Also, there is a trade-off between the assembly, which produce more compilable code, but in the high-level representations produce more functional correct. Also, that we can see that the Halstead metrics are a stronger predictor for the compilation difficulty, and we can say that there is no universal optimization that fits for all the tasks. So basically, that's my presentation for today. If you have any question about the presentation, you can ask now. Thank you.
Thank you.
I try to be quick because, you know, we are out of time, so but you have any question?
Thanks a lot. Now fish can ask many questions. Any question in the room? Yeah, please go. State your name and institution. Simone from ERCOM.
Thanks for the introduction. Simone from ERCOM. Did you run any statistical test to verify if there was a statistically significant difference in your results?
Okay, yes, I missed to name it, but we can see that, sorry, this area in the graphics means the 95, I don't remember the word, sorry, but the variance of the LLMs. I mean, don't change that more. I mean, for the cyclomatic complexity.
But did you run any statistical tests to verify?
In this work, no, but in the future we are doing it.
Okay, thanks. I have no other questions.
Thanks.
Other question? I may have one. So you show that different representation are good for different things. Did you try to just do some kind of hybrid approach and give the ASM and the high-level representation, for example, both at the same time, so that the LLM can have all the information?
Sorry, could you repeat?
Did you try to feed the LLM with different sort of, both low-level information and high-level information?
Yes.
So you tried?
I try. Sorry, I don't understand the question. Could you rephrase also? That I don't hear you very high, so.
Sorry. You show us that if you take low-level, take low-level representation, it's complementary and it's different than high-level representation. So did you try? Did you have some experiment with both representation at the same time?
No. No, we didn't. We just execute every intermediate representation alone.
Okay. Any last question, maybe? Okay, so thanks the speaker again.
Thank you.